So here we are, continuing using the sum and difference formulas for sine and cosine to find exact values for things. So suppose, for the sake of argument, that the sine of alpha is 1 over root 2, and alpha is in between pi over 2 and pi. Also, the sine of beta is negative 1/3, and beta is off in the third quadrant. Okay, so alpha is in the second quadrant, and its sine is 1 over root 2. Beta is in the third quadrant, and its sine is negative 1/3. Can you find cosine alpha, cosine beta, cosine of the sum, and sine of the sum? I would point out before you pause and work through this, part A and B are not really from this chapter. It's stuff we did back in chapter 6. However, you need them in order to do parts C and D, which are from this chapter. So pause here, use chapter 6 techniques to answer part A and part B, then use the sum and difference formulas for sine and cosine to do part C and D, and pause here. All right, hopefully we worked through it. So let's get to it. So for the first one, we know we're in the second quadrant. Okay, so place the angle in the second quadrant. They're going to go ahead and do their non-unit circle approach. So the sine is height over radius. So they've made the radius root 2 and the height 1. And because we're in the second quadrant, I know that this is positive and that this length here should be considered negative. So we're in quadrant 2. Great. I can use the Pythagorean theorem to find the missing side length. So the missing side length is 1, and we should be considering it negative, so that's why they've labeled this point as negative 1. And we were supposed to find the cosine of that angle. That's going to be the horizontal component over the radius, negative 1 over root 2, which simplifies to negative root 2 over 2. With this particular example, you could have indeed recognized that the sine of alpha is 1 over root 2. That's a number that we actually know how to deal with. We would typically call that angle pi over 4, but since we know we're in quadrant 3, this is actually 3 pi over 4. And we just know the cosine of 3 pi over 4 is negative root 2 over 2. So maybe you just did it that way. That's also fine. But for part B, that won't work. They're just doing an alternate way of doing it. I just want to skip to part B. For part B, you're not going to be able to use any known angles because we don't know any angles whose sine is negative 1/3. What if you just said beta is the arcsine of negative 1/3? What's wrong with this? There is something wrong with it. We were told beta is in quadrant 3, but arcsine is going to produce something either in quadrant 1 or quadrant 4. So as long as you resolve that ambiguity, I suppose this is okay, but it's not necessary to do it this way, and that just adds extra steps. So let's just follow their non-unit circle triangle approach. We have a height over radius of 1/3, but we're in quadrant 3, which means the height and the horizontal component should both be considered negative. So I call this 1 over 3, but I acknowledge that this is in fact negative 1. Okay. Then we use the Pythagorean theorem to find the missing side length, and we get root 8. But we know it's supposed to be negative, so we're going to call it negative root 8. So that's this length right here. And then we were asked to find the cosine. That's just going to be horizontal component over radius. Horizontal component was negative 2 root 2, and the radius was 3. So there it is. Alternately, you could just go right from the Pythagorean identity. Sine squared beta plus cos squared beta equals 1. So cos beta is plus or minus this, but since we know we're in quadrant 3, I know I want the cosine to be negative, so we take the negative 1, and then we would just compute it and get the same result. That's a totally legit way to do it. You just have to be a little careful here, because really when you start with the Pythagorean identity and solve for cosine, you'll get plus or minus, but in this problem we were in quadrant 3, so we know we actually want the minus 1. Okay, but either way, we have found part A and part B, we found the resulting bits. So now we can use the sum formula for cosine, which is right there. So we were given or found each of the following. We were given sine beta and we found sine alpha. We were given, I think, cosine alpha and found cosine beta, although it may have been the other way, I kind of forget. But there's all the values we got. Notice we have a common denominator of 6. And if you expand out that top and simplify everything, it's going to be 4 plus root 2 over 6. So even though we don't know the exact values for the angles, we do know that the cosine of alpha plus beta has to be exactly 4 plus root 2 over 6. And for part D, we would use the sum formula for sine. It's more or less the same thing, just with different pieces in different places, but it's a very similar process. So we substitute in all the values we know and got that right there. So here's a question. We were given, if I remember correctly, alpha's in quadrant 2 and beta's in quadrant 3. What quadrant is alpha plus beta in? Well, its cosine is definitely positive, and its sine is negative. 4 is much larger than root 2. So the sine is negative and the cosine is positive. That places it in quadrant 4. It's not a guarantee that a quadrant 2 angle plus a quadrant 3 angle is always in quadrant 4. I mean, it just happened to work out in this case. Okay, but the cosine was positive, the sine was negative, so it's got to be in quadrant 4. Now, we can take these sum and different formulas and start establishing more and more identities. But the process is basically the same. Pick the side that's complicated, use stuff you know to get to the other side. Here, it's maybe a little ambiguous which side is more complicated, because the left just has sines and cosines, but the right has those cotangents. However, I would say the left is more complicated because it's got that alpha minus beta, which means I also know I'm going to use a difference formula for cosine. So yeah, we start off by using the difference formula for cosine in the numerator. We're going to split that up into 2 fractions. Why would you do that? So remember, you know the end of this problem has to look like this. Of everything we could have done, why did we do what we do? We know we want something plus something else. And now we have one fraction that has a sum. So we can break that up into the sum of 2 things, and we know we want the sum of 2 things. Even more specifically, I want the second term to just be a 1, and that's exactly what we're going to get here is 1. So that's why it's easier to simplify something than to complicate it. Of everything we could have done, because we know where we're trying to get, it's kind of suggested what we're going to do. And indeed, that second term simplifies as a 1, and I can factor that as cos alpha over sine alpha times cos beta over sine beta, which is exactly the cotan alpha cotan beta we wanted. So I'm just going to clear a bit of space and show how else we could have done this. It's exactly the same steps, but in slightly different order. So the first thing I would do is exactly what is done. Apply the sum or difference formula. Sorry, sine alpha, sine beta. So if I apply the difference formula for cosine, we get cos alpha, cos beta plus sine alpha, sine beta over sine alpha, sine beta. And I happen to know I want to get cotan alpha, cotan beta plus 1. So the way I would approach this problem would be the same as the book so far. I'd be like, oh, I want that plus 1, and I know I can get it if I split this apart. So cos alpha, cos beta over sine alpha, sine beta plus. So this so far is exactly the same thing the book did. I'm about to change it ever so slightly. It's not really a big change. Okay, I want to save some space, and I'm just going to say this is cos alpha, cos beta over sine alpha, sine beta plus 1. I'm just doing that simplification. And now maybe I sort of am not sure what to do. What you can do is go down to where you want to get and start doing manipulations on it and see if you can get them to meet up in the middle. Okay, so there's still like a big gap. I don't know that the top is going to equal the bottom, but what the bottom definitely equals is cotan alpha is cos alpha over sine alpha, and cotan beta is cos beta over sine beta. And now I can recognize that, aha, I do have the same thing, and these are definitely equal. So it's legitimate to work forwards from one end and backwards from the other, as long as you do not claim they are equal until they have reached the same thing. Okay, so let's go on. That's going to be the last example we do in this video, but if you come on back, we're going to learn sum and difference formulas for tangent. Because of course, if we have sine formulas and cosine formulas, we've got tangent formulas.